Welcome to zero-dimensional space. There is no thickness in any direction, so the only geometrical thing that can fit in here is a point. There's nowhere to go, no room to make any other shapes. And that makes me sad, because I like shapes. So let's add a dimension. Okay, now I have some more room, and we can place a bunch of points at different positions, and we can connect them to make line segments with whatever length we want. This would be a one-dimensional polytope. And okay, what about a line that stretches infinitely in both directions? Or what about a line that connects to one point but like stretches infinitely in the other direction? And yeah, that's about it. It turns out one-dimensional space isn't that exciting either, but that's okay. All we need is a second axis of freedom because in two-dimensional space, there are a lot more options. We can make actual tangible shapes now, like uh, uh sorry about that. I had to disable the other dimension so I could film this section, and I didn't expect it to like squish me like that. Anyway, here's a two-dimensional polytope. It's made up of a bunch of one-dimensional polytopes connected by zero-dimensional polytopes to form a closed-off region. These names are kind of a mouthful, so let's call these one-dimensional polytopes sides, and let's call the whole thing a polygon. This thing over here is also made of one-dimensional shapes connected to zero-dimensional shapes, but it doesn't form a closed-off region. It's not really a shape as much as it is a bunch of lines, so this one is not a polygon. And even with just two dimensions, there are so many options for what we could construct out of points and line segments, and we could honestly spend hours and hours aimlessly finding more and more polygons in two-dimensional space with no real goal in mind. So instead, let's give ourselves a name. What are the best two-dimensional shapes? Now obviously that's very subjective, but one thing I happen to like is rotational symmetry. Polygon has rotational symmetry if you can rotate it and have it look exactly how it did before. So like this polygon, for example, can map onto itself in 3 different ways. So we say it has threefold rotational symmetry. This property just makes me feel tingly. I love the uniformity of a shape that looks the same in different orientations. So my question is, how do we maximize rotational symmetry? Well, for a polygon to map onto itself, its sides will need to map onto other sides, and they can only do that if they're the same length. So to maximize symmetry, we gotta maximize the number of sides that are the same length. But what else do we do? What are the other things that we could all make the same? Well, this polygon's sides are all the same length, but it doesn't have symmetry. So instead, let's try looking between the sides. After each side, the next side is going to be going in a different direction. Problem is, the change in direction is different each time. So like this one goes to the left, but the next one goes sharp to the right. The change in direction between two sides is called an angle. And once again, maximizing the number of identical angles seems to maximize uniformity as well. So if we make a polygon where all the sides are the same length and all the angles are the same, will it have all the rotational symmetry? Let's try it. Let's take 2 line segments with the same length and try to make a polygon where all the angles are the same. Yeah, I don't think that worked, but as it turns out, if we take 3 identical line segments and then do a motion like this, where we change all the angles at the same time so they're always identical, there is an angle that closes the shape and creates a polygon with, threefold rotational symmetry. And that's okay, it only has 3 sides, so each side will only be able to map to all the other ones. If we try it with 4 line segments, we can make a polygon with 4 sides and 4 angles, and this one has 4-fold rotational symmetry. If we do it with 5, now it's 5-fold. And there's really no limit to how far we can go. We could make a polygon with like 30 identical sides and 30 identical angles, and it will have 30-fold rotational symmetry. This series of polygons with an ever-increasing number of sides displays the most uniform and symmetrical polygons you could have in 2 dimensions. These, my friends, are the regular polygons. Okay, that was a lot of explanation for something you probably realistically already knew. Welcome to Polytopics, where we teach you about shapes. This is a triangle. It has 3 sides. This is a square. But the reason I'm talking about this is to establish a baseline, to explain why we classify these polytopes the way we do. Polygons with identical sides and angles are called regular because these are the shapes that maximize symmetry. And given what we've talked about so far, how would we extend the concept of a polygon to 3-dimensional space? Well, if we recall, 1-dimensional shapes were made by connecting 0-dimensional shapes. 2-dimensional shapes were made by connecting 1-dimensional shapes joined to 0-dimensional shapes, so 3-dimensional shapes should be made by connecting 2-dimensional shapes joined to 1-dimensional shapes joined to 0-dimensional shapes. So I hope you're thinking what I'm thinking. Here it is, a 3-dimensional polytope, or polyhedron, made of 2-dimensional shapes called faces, joined at 1-dimensional shapes called edges, and they're also joined at 0-dimensional shapes called vertices. Once again, it forms a closed-off area. It's solid. Now, okay, let me jump forward a bit, see into the future a little. We'll be looking in 3 dimensions for the foreseeable future, and that's because it's the number of dimensions that this video's target audience is probably used to. Once again, there's so much to see. different symmetries, series and classifications, operations from one polyhedron to the next. I've been obsessing over these things for about as long as I can remember, and I'm genuinely so excited to take you on all sorts of journeys involving these wonderful shapes, but we've got to start somewhere. So reminder that the criteria of a regular polygon we established earlier was that all the sides and angles need to be the same. And since sides and angles are the only things a polygon can have, that's a very restrictive definition. It really doesn't get more restrictive than that. Now for polyhedra, since we got to start somewhere, I'm going to make up some criteria, making them as restrictive as possible in a similar way. So for something to be a regular polyhedron, I'm going to claim that all of its faces need to be the same, all of its edges need to be the same, and all the vertices need to be the same. After all, those are the things that polyhedra have. And additionally, since a polyhedron's faces are polygons, all the faces will need to be regular polygons. So under this definition I just made up, a polyhedron is regular if all the faces are the same regular polygon, and this will by default ensure that the edges are all the same as well. And finally, all the vertices need to be the same. Is it even possible for two vertices to be different? Yes, actually, on this shape, for example, you can clearly see that these two vertices are different, and that's because a different number of faces meet at them. 5 triangles meet at this vertex, and 4 triangles meet at that vertex. So, yeah, we don't want that. The same number of faces must meet at each vertex. Okay, so that's all well and cool, but how would we possibly go about finding which polyhedra fit this criteria? Well, we're going to need to find the potential variables. Like with regular polygons, the only variable we could change while still fitting the definition was the number of sides. In other words, if I gave you any number greater than 2, you could immediately tell me which regular polygon that number refers to. What would the variables for regular polyhedra be? I guess they could be number of faces, edges, and vertices, but we don't know which combinations are possible, never mind which ones can be regular, and besides, it tells us nothing about how to construct them or what they look like. Instead, we could look for them based on the number of sides each face has, basically which polygons the faces are, and the number of faces that meet at each vertex, because each vertex has the same number of faces around it. And this is all we need, just 2 variables. We could put them into a table, and now we could try finding, say, a polygon made of entirely squares with 3 squares around each vertex, or maybe one made of hexagons with 4 hexagons around each vertex. The possibilities are endless, or maybe they're not. I mean, some of these probably aren't possible to construct, but still. Let's look at regular polyhedra made of triangles first. Let's find the polyhedron with 2 triangles around each vertex. Okay, so just like in 2 dimensions, trying to put 2 faces around a vertex causes it to flop onto itself, so we can actually just get rid of this column completely. 3 triangles, though, do make a corner, and would you look at that? All we need is one more triangle to... After loads of discussion about what a triangle is, we have finally reached our first regular polyhedron. It's called a regular tetrahedron, which means 4 faces, because it has 4 faces. It's actually the simplest possible polyhedron. There aren't any with 3 faces. So yeah, this is just what we're going to be doing. Let's try 4 triangles around a vertex. Awesome, now we have a square-shaped opening on the bottom. We can't just fill it with a square because all the faces need to be the same, but we could attach another one of these pyramid thingies to it. Symmetry! Since it's got 8 faces, we call it the regular octahedron. Now we gotta do 5 triangles around a vertex. Put that fit there, and like that, and... Now we just put 2 of these pyramids together, and then that only puts 4 triangles around this vertex, so we can't do that. We need to add a few more triangles kinda dangling off.
But after that...
And here's the 20-faced regular icosahedron. Let's go with 6 triangles around a vertex. So on your planet, angles are typically measured in units called degrees, where 1 degree looks something like this. A degree is an arbitrary amount of rotation where there are 360 degrees in a full rotation, because I guess a long time ago someone miscounted the number of days in a year. This is like an upper limit to how much angle you can fit around a vertex. Anyway, a regular triangle's interior angle is 60 degrees, and if you have 5 or fewer triangles, since the angles around that vertex add up to less than 360 degrees, there's extra space remaining, meaning they can fold into a corner. But if you have 6 triangles, it will be equal to 360 degrees. So you'll still be able to fit them all around a vertex, but you'll have no room to make a corner out of them. The only thing you will be able to do is keep extending this thing outwards, which is cool, I guess, but you can't really turn it into a polyhedron because it doesn't close off a region. And then any more than 6 triangles would be more than 360 degrees, so you wouldn't even be able to fit them around a vertex. So what this means is these are the only 3 regular polyhedra that are made out of triangles. In other words, we can eliminate all the other squares over here. But that's okay, that just means we get to check squares now. Let's get right to it. 3 squares around a vertex forms a corner. Absolutely wonderful. Let's just throw 2 of these things together, and what do you know? We get a polyhedron with 6 faces, so it's called a regular hexahedron, although it's also called a cube if you're a normal person, and I mean, I'm pretty normal, so that's what I'll be calling it. Anyway, 4 squares around a vertex, and yep, never mind. So once again, that means we've already run out of polyhedra to make out of squares. Didn't really last long, but complaining will not help, so all we can do is rule out the rest of these squares and move on to polyhedra made of regular pentagons. You probably get the gist by now. 3 pentagons around a vertex works, and this time we'll need a few more of these. Put them together like that. Remember, each vertex needs to have 3 pentagons. And there you have it. 12 regular pentagonal faces, so it's called a dodecahedron. Then we gotta try 4 regular. It's already more than 360. They don't even fit this time. So once again, we have run out of regular polyhedra. I'm starting to think we're not going to get very many more of these. I mean, we didn't even get a tiling this time, but we just gotta keep on trying till we run out of cake. 3 hexagons around. Are you serious? 3 hexagons around a vertex and we already just get a tiling. We can't make any regular polyhedra out of hexagons. I get the feeling we're not going to see any more, but I just 1, 2, 3. All right, okay. So heptagons just don't work. And these interior angles are only going to get bigger as the polygons get more sides, so we also can't fit 3 octagons around a vertex or any regular polygon with more sides. So you know what that means. Tetrahedron, cube, octahedron, dodecahedron, icosahedron. Now I hope I've made it clear that I'm obviously not actually the discoverer of these. I was beaten by a few thousand years. I just believe that pretending to discover something for the first time is an effective teaching method, and I hope it helps you understand why I just really like these shapes. They're so simple and so uniform and so systemic. And you want to know who also really likes these shapes? Find out the answer to that and more in the elusive first installment of Polyhistory. I am not doing that jingle again. Realistically, they were most likely independently discovered by multiple different people in multiple different places at multiple different times, which is fair enough, I guess, but today they're most commonly associated with a Greek philosopher named Plato, which gives them the common name, the Platonic solids. And that's because Plato proposed that these polyhedra were the building blocks of the universe. The tetrahedron was fire because it has sharp corners, the icosahedron was water because it can roll, the octahedron was air because, I don't really know. The cube was Earth because it can stack. Okay, I guess that one kind of makes sense. But there's still the dodecahedron left. So Plato's idea was that it must be those funny looking dots in the sky. In case it needs to be said, I'm not legitimizing any of this. It's pseudoscience. On one hand, science has changed so much from people discovering new things that even something like Johannes Kepler's Mysterium Cosmographicum, suggesting that the orbits of the planets of the solar system can be modeled using nested inscribed spheres and regular polyhedra, went out of date when that same person realized that the solar system's orbits are not actually circular. But on the other hand, mathematics has changed so little that a book that describes the regular polyhedra from thousands of years ago is still relevant today. Unfortunately, the Platonic solids are not actually fundamental to the fabric of the universe, but that doesn't mean you wouldn't be able to find them on your planet. For example, they happen to be very useful for dice. Since all the faces are the same, all of them have an equal chance of being rolled, and that's why you are probably intimately familiar with these shapes if you play Dungeons & Dragons. And they also show up in like a few other places and stuff. Humans are weird. Why are they the target audience for this video again? Alright, because humans love these shapes. Artists and sculptors and architects have been depicting the Platonic solids in their work because people are compelled by their symmetries. Wait, symmetries? What kinds of symmetries do these polyhedra have? Do they also maximize the... I gotta figure this out. So a polyhedron's rotational symmetry is basically how many ways it can map onto itself. Like, okay, let's try it with a cube. You can imagine that there's a copy of the cube here that's kind of frozen in place. How many ways are there to rotate the cube so that it fits this thing? Well, first you gotta pick which face should go on the top, and there are 6 faces, so that's 6. And since a square has 4 sides, there are 4 different rotations you could have with any given square on the top. That's 4 rotations for 6 squares, so that means the rotational symmetry of a cube is 6 times 4, which is 24. I have no idea what to do with this information. But whatever, let's try it with the octahedron, I guess. 8 faces and they're triangles, so 8 times 3 is also 24. Wait, okay, that's a bit weird. Alright, I'm gonna put them side by side and... they have the same symmetry! So in my opinion, the best way to visualize the relationship between the cube and the octahedron is to put them inside each other. I will say that this doesn't actually work for most other polyhedra, so I wouldn't get too comfortable with it, but it works for these, and I still think it's a good way of understanding it. So if you put an octahedron inside a cube like this, you can make it so that every vertex is in the exact center of one of the faces of the cube. The faces of the cube correspond perfectly to the vertices of the octahedron. And the same thing works the other way around. Put a cube inside an octahedron, and once again, the faces of the octahedron correspond to the vertices of the cube. The cube has 6 faces and 8 vertices, and the octahedron has 8 faces and 6 vertices. They do a switcheroo. And remember that table from before when we used those two variables to arrange them? Look, the cube has 4 sides on each face and 3 faces around each vertex, while the octahedron has 3 sides on each face and 4 faces around each vertex. These values swap too! Both of these polyhedra have 6 fourfold things and 8 threefold things. The only difference is that they flip-flop the faces and vertices. Other than that, they're like basically the same shape. This relationship is known as duality. We say that the cube and the octahedron are duals of each other. Oh yeah, we're going to try this with the other solids. Let's find the dual of the dodecahedron first. And now we know how to find it. We just gotta do that number switcheroo thing. We already know it has 12 faces, it has 1, 2, 3, 4, 20 vertices, and on the table, 5 sides on each face and 3 faces around each vertex. Just as before, we flip-flop these values. And this flip-flopped version has got to represent the icosahedron, right? Oh, you bet your sphenocorona it does. All the relationships between the cube and the octahedron also apply to the dodecahedron and the icosahedron. If you work it out, they both have 60-fold rotational symmetry, and if you put them inside each other, the faces of the dodecahedron correspond to the vertices of the icosahedron, and the faces of the icosahedron correspond to the vertices of the dodecahedron. These two are also duals of each other. But that still leaves the tetrahedron. What's the dual of the tetrahedron? Honestly, you could probably figure it out if you've been paying attention, so I'll just shut up for a bit and let this speak for itself. Yep, the tetrahedron is the dual of the tetrahedron. It's a self-dual. And this is another reason I like to arrange these polyhedra into a table like this, because you can visually see another bit of symmetry. If we draw a line here, you can see that each polyhedron is diagonally across from its dual, because of course they are. The two values here are swapped. 4, 3 is diagonally opposite from 3, 4. And wait a minute. If you look at it this way, don't these tilings look kind of symmetric as well? It kind of looks like these two would be the duals of each other, and then that one would be the dual of itself. Oh, don't tell me. One last look at the tiling of triangles. Let's imagine putting a vertex in the middle of each triangle and connecting all the adjacent ones, and oh, look at that. Each triangle corresponds to a vertex of the hexagonal tiling, and then each hexagon corresponds to a vertex of the triangular tiling. I mean, the switcheroo for the number of faces and vertices is kind of irrelevant here, but the other switcheroo thing still happens, and it makes perfect sense too. These two tilings still function like duals of each other, even though they're not even solids. Okay, square tiling. Put a vertex in the middle of each square, connect them, it's another square tiling. It's the dual of itself. It just all works out. I love shapes! Duality is just one of the many different relations between polyhedra that make them a constant source of virtual serotonin to my antenna, or maybe hair, I don't actually know what these are. And if you're wondering when I'm going to make the next video in this series, well, this one already took me way too long to make, and I don't even know if anyone's going to watch it, so I don't know. Some other time.